Lab 2, Projectile Motion. The purpose of this lab was to analyze and compare the motion of a projectile from experimental data against predicted data models with drag and without drag. Using Newton's second law equations, we could accurately predict and update the ball's velocity and position. To use these equations, we had to calculate the net force on the ball with the effect of air resistance and without. In the final graph, I compared the experimental trajectory against the two predicted models, F-net being just gravity and F-net including drag. After analyzing the data, I could conclude that the computational model that included drag was more accurate to the experimental data than the one that only accounted for gravity. I used Newton's second law equations shown to the right to calculate the velocity and position of the ball at each time interval. By applying the momentum principle, we can see that the change of position and time of the ball based on different net forces. Net force is calculated by adding up all the forces acting on the object in a certain direction. It changes based on momentum, which is changed in part based on velocity, which is change in distance divided by change in time. Momentum is mass times velocity, and net force is change in momentum over change in time. Acceleration in these equations is the net force divided by the mass of the object, so net force has a direct impact on the change in velocity, which directly affects the change of position. For projectile motion that does not account for air resistance, the net force is constant and only consists of gravity, but when air resistance is accounted for, drag force needs to be factored into the force equation. As shown in the image below, drag acts in the opposite direction of the motion of the object, so it affects the net force in both the y and x direction for projectiles. The constant b in the equation above is proportional based on experimental data. In many scenarios, we don't account for the effect of drag, but that does not mean it is always negligible. We can predict that a model that accounts for drag will be more accurate than one that does not, since it is closer to the true net force in the real world. Though in this case, the model with gravity is fairly accurate. One that accounts for air resistance through drag force will be better, though. For this experiment, the system is the moving paper ball, and the surroundings are everything else in the video, such as the meter stick, floor, wall, person, and anything else near the ball. The initial conditions for the lab are that the ball starts at its initial velocity 2.02 meters per second in the x direction and 0.826 meters per second in the y direction, and its position starts at the origin. In this experiment, we threw a wadded paper ball to act as a projectile. I then analyzed the video and tracker to get the experimental data and identify the initial conditions. Then, using the initial conditions, I made two computational models to compare the results to, one that included the effect of drag and one that did not, and only included gravity. Because of the time, x position, and y position data obtained from tracker, I could graph the actual trajectory of the ball. Through coding, I was able to make two computational models to predict the trajectory of the ball. One computational model set the proportionality constant b to 0, so F-net is equal to only the force of gravity. The other model included the force of drag in the F-net calculation. Through trial and error, I found that when b equals 0.0001, the predicted trajectory was very similar to the actual trajectory of the ball. I used the drag force formula explained earlier to calculate the F-net vector in both models shown directly to the left. This calculated F-net value, when then plugged into the velocity update formula, which is also used in the update position formula, was looped on a set time interval, so the different x and y positions could be graphed to analyze the effect of drag on the predicted trajectories. Here are the outputs of the two prediction models for drag and without drag. And here is our final graph. And as you can see, the yellow drag model is closer to the blue experimental model, more closer to it than the gravity is. The graph shows that when b equals 0.0001, the model with drag is more accurate to the experimental data, and the trajectory of the ball with only gravity is close but not as accurate. This shows that the drag has an effect on the projectile motion, even if it is relatively small, and calculations that account for air resistance are more accurate than ones that consider it negligible. In conclusion, the model with drag was a better prediction to the actual data than the model without drag. A source of error could be human error when marking the points for the experimental data in tracker, since I am human and wasn't perfect. Another source of error could be in the calculations. There could also be human error in how the video was made and the phone not being able to be held perfectly still, which could throw off the data. So, for the terminal velocity question, no, neither of the models predict a terminal velocity since the maximum falling speed was not reached. An experiment that could account for this is dropping an object from a tall origin and seeing when the velocity stops increasing in the fall to find the maximum possible falling speed. And it would take the same amount of time in both scenarios for the second question, because the initial velocity is the same. Using Newton's second law, we can see that the initial force on the object is the same, and because of this, they will have the same change in momentum. The velocity update and position update equations show that the final position for the original will be greater, but the max height for the new one will be greater. The differences cancel each other out.